Okay, so we are going now to introduce something very simple, which is the reinforcing sizing diagrams. We also name that like RSD. And it has to do with the ultimate limit state of bending. So something very common in reinforcing, in reinforced concrete. So let's start analyzing a cross section. Let's be original, a rectangular one. So the height is h, the thickness or the breadth is b. Everything is, so very standard, no? So the top reinforcement is SI and AS prime. The bottom reinforcement is AS. The mechanical cover of the top reinforcement is D prime, and the distance from the top fiber to the bottom reinforcement is D. So this is all very international nomenclature. So now we are in ultimate limit state of bending. So the strain distribution, and I'm going to use the American just for simplicity. The European is a little bit more complicated. Nothing very difficult, but let's do the American. So the ultimate strain, because this is positive bending, so the ultimate strain in the top fiber is going to be 0.003. And then let's do a general strain distribution. So a general strain distribution, this is X. This is X. The depth of the neutral fiber. So any of these planes are capacity planes, so they are, all of them are the ultimate limit state of bending. But we are going to work with the generic one. So this one, the depth is X. So for this, because we are in capacity design, and we know that the top deformation, the top strain is this, 0.003, we only need one variable to fix the strain distribution. This one variable is going to be X. So if I know X, and I know that I am in the ultimate limit state of bending, then the strain distribution is fully defined. So this is, let's do another color, for example. So this is the strain of the top reinforcement, and this is the strain of the bottom reinforcement. So this is epsilon S prime, and this is epsilon S. Okay, perfect. Once I know this, and this is going to be the strain, sorry if this is very simple. This is basic course of mechanics, but okay, let's continue. So if I know the strain distribution, it's simple to get the stress distribution. Because we are going to be in the ultimate limit state of bending, I can use the rectangular distribution of stresses in concrete. So that means that I'm going to consider that is under compression only lambda x, and the value of the stress is FCD. So this is the contribution of concrete in capacity. Then here we are going to have sigma S, and here we are going to have sigma S prime. Let's put that in compression. So this is going to be sigma S prime, and this is going to be sigma S. It is very easy once you know epsilon S to know sigma S, because this is just only, for example, the bilinear diagram. So the bilinear diagram from Eurocode, so that epsilon S, sigma S. So once I know epsilon S, maybe here, I know sigma S. But because everything is defined by X, epsilon X is a function of X, epsilon S prime, and epsilon S is also a function of X, and sigma S prime is a function of X, and this is a function of X. Because once I know X, I know the strain distribution, I know epsilon S and S prime, I know sigma S and sigma S prime. Perfect. This stress distribution has to be in equilibrium. Let's do that. This is the center of gravity of the cross section. So it has to be in equilibrium with, and well, we are in capacity. So let's do here NRD and here MRD, the resistance design, so capacity. Let's write the equation. Let's write the equation of equilibrium, the equation of equilibrium. They are going to be very simple, and we all know that by heart. So NRD, the actual force, what is going to be? Is going to be FCD times what? Times lambda x times b. Okay. And then plus sigma s prime is a function of x. We all know that. Times as prime, the value of the steel in compression, minus sigma s, function of x, and then as. Okay, something happened here. And if we have the actual force, or the bending moment, sorry, MRD, so it's the same, but with the corresponding lever arm. So it's going to be FCD times lambda x times v, and now the lever arm is going to be h/2 minus lambda x/2. Yeah, so perfect. Then this is going to be sigma x, the contribution of the top reinforcement is sigma s prime function of x, as prime, and then the lever arm is going to be h/2 minus d prime. And then the contribution of the bottom reinforcement is also positive. So this is going to be plus sigma s of x, as, and then the lever arm is going to be d, no? D, right, d minus h/2. Perfect. Perfect. So one thing that we all know is the PM interaction diagram or NM interaction diagram. So the NM interaction diagram is something very simple. We all know, because all engineers, what we really know or we have in our soul is the NM interaction diagram. It's just the representation of the capacity for a cross section. So let's say AS, so we have a cross section, AS and AS prime are known, the concrete is known, the geometry is known, so everything is, so in here the only unknown is X at the right side of the equality. So here at the right side of the equality the only unknown is X, because everything is defined. So what we do is a representation of M and N that should be like something like this, for example, and something like this. Yeah? It's non-symmetrical, so if it should be like this maybe. Okay, more or less. So just giving values to X, and in this is from X to 0 to X to infinity, or very large, and then we obtain for each value of X pairs NM. So for each value of X we obtain the whole diagram. This part is for positive bending, and the one we have considered here is positive bending, but if we consider negative bending we obtain the other part. This is very interesting because if we have a bunch of combination of pairs NM, we know that the section will resist or not all this. If we have one of these out of this, it will break the section and the section will not resist this pair. So we all know that. But let's go in now at this point introduce what is the RSD. Imagine that we don't know AS and we don't know so AS prime and AS. We don't know them. And imagine that N and R are given. So in these two equations, now we have three unknowns, which are x, as prime, and as. So we can solve for as and as prime. So we can solve for as and as prime. And we discovered that once we solve for them, what we obtain are function of x. So we can say that as and as prime are function of x. So yeah, if n and m are given, I can solve these two equations for as and for as prime, and what I obtain is function of x. I can write here, solving for that. I don't know if it is worth to do it or not. It's published already, so just find in publications. We have published the solution, so don't worry. Or you can just spend time and solve for that. There's not much interest. So the idea is that you can plot here x, and here you can plot the area of steel. So, and we are going to have three plots. One, for example, is as prime, can be like this. As prime. We can have also, I'm just, for example, this. That can be, for example, as. And then the summatory of the two of them can be like this. So this is going to be as plus as prime. What we obtain is that a solution can be for as prime equal to 0 and as equal to the total area, so we only have as. Or we can, for example, opt for the symmetrical solution, but the symmetrical solution is way more expensive in money and in CO2 emissions than the minimum one, that in this case as. So we can look to all the possible solutions, because we don't gain anything. So we gain nothing if we design for the symmetrical, because the ultimate bending moment and the capacity is going to be the same. So let's do an example, because this is very useful in some type of structures. So imagine that we are doing a precast tunnel. So we have here, piece of land. We do a trench here. We do a trench here, and then we design here a precast tunnel, something like this. Then the symmetrical here. Okay, that's symmetrical. And here, for example, the roof. And here is just symmetrical. And then we fill that. So in a cross section like this, I'm going to have a huge bending moment, and a huge axial force. And many of our colleagues will say, okay, big axial force, symmetrical reinforcement. And I deal with this topic very often. So please, just use this. I know that we all love PM interaction diagram, but for cases like this, where the worst case scenario is very clear and is just likely 1 or 2 or 3 pairs NM, do an RSD, and you can see, where the minimum is. And we can save tons of steel. Actually, for example, if we do, so this is the thickness or the breadth of here, no? So that's the breadth. And we opt for the symmetrical solution. What we obtain is this depth of the neutral axis, for example. So this. So if I just don't use as prime, the only thing is that x is going to be a little bit greater. That is the only thing. So the only consequence is that x is going to be a little bit deeper. But I don't need that. Maybe because of construction, I'm going to put here some minimum amount. Okay, perfect. If I put here some minimum amount, I can go for this, for example, in AS. Okay, that's the only thing I wanted to tell to you. Thank you.